Good morning, everyone, and welcome to the Online Help Center. This is our 5th webinar, and in our 2023 series, my name is Rob Bertle, so I'm going to be your moderator today. Before we begin, I'd like to acknowledge that Thompson Rivers University campuses are on the traditional territories, our traditional lands of the Tk'emlúps-te-Secwepemc Kamloops campus and the Tulk Williams Lake campus, within the unceded and traditional territories of the Secwepemc. Thompson Rivers University and their partners host the annual webinar series and courses dedicated to providing technical information, resources, and tools to small water system owners, operators, and Indigenous small water systems on issues around treatment, regulation, operations, maintenance, and water quality monitoring. This is basically everything you do with regards to being a water quality operator. The webinars are scheduled every 2 months in 2003, and they're offered free of charge. For attendees who are EOCP certified operators, each webinar will count as 0.1 CEUs towards a certificate. A certificate of completion will be issued to the webinar participants so they can submit those to the EOCP. We will have 1 hour presentation followed by half an hour of questions, but I invite you to type your questions into the question column there so that we can answer them. I'll read them out so Pranav can answer those questions at the end of the presentation there. Today, we're going to focus on CT, disinfection. So disinfection is destruction of pathogens. It's the most important treatment step and ensures safe water quality is achieved. In this webinar, we will discuss primary and secondary disinfection, the role of CT, the products of disinfection concentration and contact time, and ensuring pathogen-free drinking water reaches the tap. Finally, I need to talk about our presenter today. Our presenter is Pranav Chintalapati, Assistant Professor of Teaching at UBC. Pranav actually has a background in chemical and biological engineering, it sounds like here. Now, Pranav has a degree Pranav, is that engineering or was it chemical engineering?
Yeah, chemical engineering, and then also environmental engineering. Yeah.
Correct. Yeah. And we were just chatting before the meeting here. He did his PhD in Boulder, Colorado, which is a really interesting town. I want to welcome Pranav, and Pranav, I'm going to turn it over to you for your presentation.
Great, thanks. So I need to share my screen. Let me see if I have hosting duties. I don't think I can do it yet.
You should be now.
Okay, perfect. And then I'm going to do that. And what do you see right now? Do you see it in full screen?
No, not yet, no.
No, okay. Let's see. And how about now? Are you seeing full screen or are you seeing like a presenter view?
We see your opening screen there and then the next slide. So I'm assuming this is presenter view.
Oh, you're seeing presenter view. Okay, let's try this again. And how about now?
We're actually seeing 2 screens there now at this point in time. We have on the right-hand side your presentation, but it's not in presentation mode.
Okay, let me stop sharing. I'll try again.
Sure.
Okay, what are you seeing now?
Again, your speaker notes and the presentation. We're seeing speaker notes and the presentation is split between the 2.
Okay, hold on, sorry. Let's see.
Now we've got 1 screen. That's good sign.
Okay, and then that's not showing you the slides in full screen right now?
That's got
It is.
slide full screen now. Yes, we're there.
Okay. And if I change it, it goes to the outline?
Yep, you're at outline right now.
Okay, perfect. Okay, so I think we're good. Thanks for bearing with that. And thanks, Rob, for the introduction. Hi, everyone that's attending. So today, like Rob mentioned, we're going to talk about CT, what CT is, what it is as a concept, how do you use it, and then also how do you determine it? What are the components that make up CT? How do you figure out what the C is? How do you figure out what the T is? And then how do you put that all together to determine the effectiveness of the disinfection that you're applying in your system? So I'll be walking us through that. And like Rob said, you might have questions that come up as we're going through this. So feel free to jot those down so that you don't forget them if we get to the end. All the Q&A part will be towards the end of this session. So you should be able to answer that. And then we can go back and refer to the slide if your question corresponds to something that was presented earlier. Okay, so let's get into the webinar here. So a few of the topics that we're going to talk about, like I said, a bit of an outline here. Just want to quickly talk about disinfection as a treatment step and what we're targeting there, how we're aiming to remove pathogens from the water to make it safer to drink. Some of the guidelines for pathogen reduction. So what are we targeting for different types of pathogens that we want to remove from the water? And then one thing we'll notice is if you look at the drinking water guidelines, they're often referring to a particular CT that you need to achieve and the corresponding log removal that comes from achieving a certain CT for a different pathogen. So that brings up the question, well, what is CT? If I look at those guidelines and it's giving me numbers for CT, what does that mean? What is that CT? So we'll talk about that, introduce the concept of CT. And then not just the concept, but how do we actually get it? First, we need to know how we get the C in CT, and then we also need to know how we get the T. And the T is referring to contact time. And so in order to do that, there are a couple different ways of doing it. And so we'll look at both of those, and then we'll look at some of the sub calculations that you need to do in order to determine what that T value is. So once we get C and we learn how do we get our C and we learn how do we get T, we'll put it together, we'll calculate what CT is, and then go back to those guidelines and look at how much log removal can be achieved for a particular CT and what that means in terms of log credits. And we'll talk about what log credits are a little bit as well. And then after that, we'll wrap things up and then get into some Q&A. Okay. So this slide basically shows a pretty conventional drinking water treatment system. Your small water systems may not have all of these components, may just have one or two of these. So I just will quickly kind of introduce what each of these things are doing. If you start at the left here, you've got a source water. It may undergo some type of screening, so you're removing some larger particles from that. You might have coagulation where you're introducing a chemical and rapidly mixing it around to destabilize any particles that are kind of stable. And the idea is that when you destabilize them, that it'll allow you through flocculation, slow mixing, to allow these small particles to come together, agglomerate, form larger flocks. Those flocks can then settle out in a sedimentation basin, and anything that hasn't been settled might get carried over to a filter of some sort. Through that filtration, you're then removing any remaining particles that are in there, and then that filtered water might then get some disinfection. And disinfection can happen in a few different ways. You could be adding chlorine, you can use UV, you can use ozone, all for the purpose of removing pathogens from water. So the point of showing you all this is just to kind of indicate that although there are a lot of steps in a treatment process, a lot of it is focused on particle removal. And in that process of removing particles, you may remove some pathogens, some that are adhered to particles, some that might get removed during coagulation or flocculation, some that might get settled out or filtered out. But the large majority of pathogen reduction is going to happen during disinfection. And that makes disinfection super important because that's the step where we're making sure we've removed the microorganisms that can make people sick. And if you look at this, I've got disinfection as primary disinfection, and then I've got another disinfection here called secondary disinfection. And in the middle between these two is the clear well. You might call that a contact basin or a contact tank. It's a place that your water can be stored after it's been disinfected and before it gets sent off to distributed to people's homes. And so with primary disinfection, what we're really aiming to do is destroy any pathogens that are in the water. And like I said, you can use UV, you can use chlorine, you can use ozone for that. And then in the clear well, the water is in contact with whatever we've added. And then for secondary disinfection, it's really about ensuring that you don't get any regrowth and you continue to protect the water as it gets sent along to people's homes to ensure that we don't get any additional microorganisms either entering into that distribution system from other locations like leaks and things like that, or also just regrowing along that distribution line. So we're going to talk a little bit more about primary secondary disinfection. Like I was saying, with disinfection, we're really targeting microorganisms that can make people sick, specifically bacteria like E. coli, viruses like adenovirus or protozoa, which are things like Giardia and Cryptosporidium that you may have heard of. And then with primary disinfection, just to reiterate, like we said, we're treating those pathogens in the water at the treatment facility or the treatment system. And that could be chlorine, it could be UV, it could be ozone. And with secondary disinfection, we're making sure that those pathogens, the bacteria, the viruses, the protozoa, are not regrowing, and they continue to treat the water in the pipes as they get to people's homes. And you may have heard in other classes, people refer to a chlorine residual. So it's really about maintaining that residual and ensuring that there is some amount of chlorine in that distribution system in order to protect the water as it goes through. Okay, so for the concept of CT, I'm primarily going to talk about a chemical disinfectant, and we'll just use chlorine as our main example because it's primarily common. You can have a version of CT when you have UV as your disinfection system, and it's called IT. I'm not going to be covering that in today's webinar, but if you have questions about that, my email was on the title slide, and I can go back to that, or I can share it with the organizers, and you can feel free to send me an email. We can talk about IT as well. Okay, so that's primary disinfection and secondary disinfection. Some of the things that we're trying to treat here, we mentioned viruses like adenovirus. This is what an adenovirus looks like, or cartoon of what one looks like. Bacteria, this is E. coli. Protozoa, I think this is Giardia or Crypto. I can't remember which one this is. But a couple things to indicate. So one, size-wise, this isn't to scale, but you do see viruses as being smaller than bacteria. Bacteria a little bigger than viruses. Protozoa a little bigger than bacteria. And the way that chlorine, in this case, works in treating these pathogens is almost the same. It enters through the cell wall, it penetrates kind of this outer shell that exists for each of these, and it attacks what's going on inside. And by attacks, what I mean is that it starts reacting with the proteins, the DNA that exists within these microorganisms. It starts oxidizing them, reacting with them, and basically rendering them ineffective. And when they become ineffective, it means that these microorganisms can't infect you if they're consumed, or they also can't replicate if it's affecting the DNA. And so for those reasons, we achieve disinfection as a result of the contact or interaction between our disinfectant, which could be chlorine, and the microorganism itself. So it's really important that we make sure that our disinfectant has time to get into contact with the microorganisms in order to actually penetrate into the cell wall and start damaging what's going on inside there so that these things don't make us sick. And chlorine, for example, with viruses and bacteria is actually really effective. It can get in through the wall, it can damage what's going on inside there quite well. When it comes to protozoa, it's actually a little bit harder because this outer shell is quite thick and hard to get through for chlorine. So in order for chlorine to get through and disinfect protozoa, one thing you'll see if you look at the guidelines is that the CT that's required for protozoa would be a lot higher than it is for bacteria and viruses. So we'll look at some of those numbers and we'll get into what it means to have a higher CT. Just as a counterpoint, UV, for example, is actually quite good at getting into protozoa because it can easily, those light rays, those UV rays, they can actually get right through the wall of a protozoa and attack what's going on inside without much difficulty. And so, for that reason, protozoa actually are quite susceptible to UV. And so sometimes having a combination of both is quite good. So that you can maybe do primary disinfection with UV and then have chlorine and a residual in your distribution system. It tends to be a good combination. But if you don't, you can still treat protozoa with chlorine. That's totally fine. You just need to be conscious of how much CT that you need in order to do that. And what do I mean by how much CT? That's what the kind of point of this webinar is. So we'll talk about that. Okay, so we talked about viruses, protozoa, and bacteria and the different types. So there's guidelines for how much of those need to be reduced in drinking water. And it depends on the type of water that you have in your system. So if you have surface water, then for viruses, we're looking at a 4 log removal of viruses. Now, log as a concept, the word, it means, it's short for logarithm. And really what that means is how many factors of 10 you're trying to reduce a particular pathogen by. So if we want 4 log removal, it means we want 10,000 times the removal, which is 10 to the power of 4 is 10,000. So we want 10,000 times removal of our viruses. Another way to think of that is if you have 10,000 viruses, through our treatment, we want to reduce that from 10,000 down to 1 virus. Similarly, if you have 3 log removal, we require a 3 log removal of Giardia or protozoa. If you have 10,000 little Giardias or little cryptos in your water, then a 3 log removal means we want to take that from 10,000 down to 10, or reduce it by a factor of 1,000. Another way to think of that is just in terms of percent. So 4 log removal means 99.99% reduction. 3 log removal means 99.9% reduction. If you follow that pattern, you think 2 log removal, 99%, 1 log, 90%, and so on. So our guidelines for viruses are 4 log removal, guidelines for Giardia and crypto, 3 log removal. And then for bacteria, we just want no detectable E. coli or total coliforms and fecal coliforms. That's our guideline for bacteria here. You might remember or might have heard of surface water having a 4-3-2-1-0 rule. So I've just isolated the ones related to pathogens, so viruses, protozoa, and bacteria. In case you're wondering what happened to the 2 and the 1, I just put it as a footnote here. So the 2 refers to 2 forms of treatment. So you want 2 barriers or 2 forms of treatment. So for example, filtration and disinfection are 2 forms of treatment. And the 1 in the 4-3-2-1-0 rule refers to turbidity. So less than 1 NTU of turbidity. NTU, if you're unfamiliar, it's called a nephelometric turbidity unit. It just means how cloudy the water is. So bigger number in NTUs means more cloudy water. And as you get lower and lower in your NTUs, it's just less and less cloudy. So less than 1 NTU means that your water is pretty clean, pretty clear. Okay, so that's the 4-3-2-1. And so for surface water, that's what we're aiming for in terms of viruses, protozoa, and bacteria. If you're using groundwater, there's a couple of classifications depending on what your groundwater is. If it's considered a GARP, which is groundwater that's at risk of pathogens, then in that case, you basically need to follow the same requirements of surface water. If it's at risk of having pathogens, then you follow that 43210 rule, which is the same thing we talked about up here. Some groundwater might be classified as viruses only, and in that case, you're only concerned with the 4-log reduction of viruses. Okay, so it just depends on how your groundwater is classified, and that might be informed by an environmental health officer or a drinking water officer that supports your system. Okay, so those are our guidelines for pathogen reduction. And so we talked about UV, we talked about chlorine primarily. I just wanted to show you this table which looks at the effectiveness of different disinfectants. And we'll hone in on this free chlorine one, and maybe we'll do a quick comparison with UV. So what we're seeing on the side here is the required CT. And the thing that you want to just think about is if something is showing up higher on this list, it means that it is a little bit harder to treat with a given disinfectant. So in this case, with free chlorine, adenoviruses very effectively treated by chlorine. So the required CT in this case is quite low. E. coli, bacteria, also relatively low. And like we were saying before, protozoa, because of that hard outer shell, it's a little bit harder to get that chlorine into there. So there's a higher dose or CT that's required to get that crypto. Interestingly, with UV, like we were saying, is effectively treated, protozoa is effectively treated by UV at a lower dose, in this case IT. So, so just wanted to indicate that. But again, we're talking about CT. You've heard me mention CT a few times. I still haven't talked about what it actually is. All I'm doing is giving you some indication that it has to do with the effectiveness of your disinfection, has something to do with how much disinfection you need or disinfectant, concentration you might need. So let's get into what CT actually is. So the concept of CT is really a combination of two things. It's the concentration of the disinfectant, so that's what the C is, and it's the amount of time that that disinfectant is in contact with the water, and that's the T. So C is the concentration of the disinfectant, T is the contact time between the disinfectant and the water. So think back to that picture of the different pathogens. Not only does it matter how much disinfectant or chlorine that we have in the water, the concentration that we're supplying, but also the amount of time that it has in contact with the microorganisms so that it can effectively break through that cell wall and damage what's going on inside there. And so because both of these things are important, we actually multiply these two values and use that to come up with a new term, which is CT, which is a constant value that's required to achieve a specific level of disinfection for a pathogen. And so it's going to be specific to each pathogen. So for example, if you look up the guidelines, and we'll look at a couple tables in a second, you're going to see CT requirements for 3-log removal of Giardia and a different CT requirement for 4-log removal of viruses. So depending on the water and the targets that you're having, you're going to need to ensure that you're meeting the log removal to meet those guidelines based on the CT that you have. And that could require increasing or changing the concentration of the disinfectant, or it could require changing the amount of time that that disinfectant spends in contact with the water. Okay, so like I was saying, CT values are determined for a specific pathogen. So if you look in the drinking water guidelines document, you might see tables that look like this. This one, for example, is showing CT values for 3-log removal of Giardia. So you've got, in this case for chlorine, you have different chlorine concentrations, and all these numbers between 137 and 451 in here correspond to CT values. That's the combination of multiplying the concentration by the contact time. And that value is indicating what is required under certain conditions in order to get 3-log removal of Giardia. Okay, so what are some of the conditions that we care about? Well, 2 things that we need to note is that temperature and pH both affect the CT values. And that's because both of those things affect how well a disinfectant works. So you might have seen another webinar or taken some classes related to disinfection and seen a table that looks like this. So in the case of chlorine, one thing to note is that the species of chlorine that you have is going to vary depending on the pH that you're operating at. And so if you're familiar with the chemistry of chlorine, you may be familiar with this hypochlorous acid, HOCl, and its counterpart, which is the hypochlorite ion, which is the OCl minus. And so these things are in differing proportions depending on the pH. So if you're at a pH that's lower than 7.6, then you're going to have predominantly the hypochlorous HOCl acid there. And if you're at a higher pH above 7.6, then you're going to have more of this hypochlorite OCl minus ion that is predominantly present there for your free chlorine. If you're right at 7.6, that's known as the pKa. So that's when you have equal parts of both. Why does that matter? Well, the reason it matters is because HOCl is a more effective disinfectant. And so because of that, your disinfection is more effective when you're at lower pHs. So chlorine works better when your pH is lower than 7.6 because you're predominantly relying on hypochlorous acid to do the majority of disinfection. And the rate at which this disinfects microorganisms, the HOCl, is much higher than when it's OCl minus. And so for that reason, if we look at a table in our guidelines, so again, this is looking at CT value. So all of these numbers underneath this blue heading here, all of these numbers from 23 to 316 are different CT values. For the inactivation of Giardia, we'll get into temperature in a second, but all you need to look at is see that if your pH is less than 6 versus if your pH is 6.5 versus if it's 7 versus if it's 7.5, the thing to realize is that the numbers are getting bigger as the pH is increasing. What that means is the amount of CT that's required is increasing as pH gets bigger. And what that means, because CT is either the concentration of your disinfectant or the contact time, what that means is that as your pH is increasing, you need more disinfectant in place in order for it to achieve the 3-log removal of Giardia. Okay, so the main takeaway here is that pH affects the effectiveness of disinfection. And so because of that, as you go towards higher pH values, you might need more CT in order to achieve the same amount of disinfection. So that's with pH. The other thing is temperatures. So we've looked at this table. This is for 0.5 degrees Celsius. The other thing to note is that in general, when you have higher temperatures, the reaction rates, the speed at which a reaction occurs between a disinfectant and the stuff inside of a microorganism also increases. So increased temperature actually promotes faster disinfection. And so because of that, it's harder to treat water that, at least disinfect water, that is colder than it is for when water is a little bit warmer. So there might be some seasonal variation in the CT values. And in this case, we can see that when we look at the same table, but instead of 0.5 degrees Celsius, we're now looking at 25 degrees Celsius. And what you see is that the CT numbers are way lower. So the conditions are the same. It's the same pH values across the top of both of these tables. But now that our temperature is higher, we don't require as much CT in order to get the same inactivation of Giardia. And that's because at higher temperatures, we are able to get a more effective disinfection when we're using chlorine. So that's what these notes on the side are basically just describing. So we can pick a random number, let's say 2 log or 3 log in activation. Let's say 3 log in activation at a pH of less than 6, and you have 0.6 concentration of chlorine, so that's 141. The exact same thing at 25 degrees Celsius is a CT value of only 25. So you can see that's a big difference just by when your temperature is higher. So increasing temperature generally leads to more effective disinfection, which means a lower CT that's required. Okay. So we talked about how CT is temperature and pH dependent, but how do we actually get CT? Like, where are those numbers coming from in those tables? How do we know where our system is relative to those numbers in order to know how much log removal we're actually getting? Okay, so C is the concentration of the disinfectant, and where you want to measure C is actually at the outlet of your clear well or your contact basin. So even though you might be adding chlorine ahead of that, and your contact tank is where that chlorine is interacting with the microorganisms in the water and having a chance to disinfect, you want to measure C, or take a sample to measure C at the outlet of your contact basin before it then goes off and is distributed to go to people's homes. The reason you want to do that is because we want a conservative estimate of the concentration of chlorine that's in the contact basin. And if you just use what's going in, you're not accounting for the fact that that chlorine is going to react with all the stuff that's in the water. And as it's reacting, it's going to reduce its concentration. And so what that does is actually give you an overestimate of the concentration of chlorine that's in the contact basin, if you just use what's going in. So to be on the safe side and to err on the side of caution, what you do is you measure it at the outlet. And if you want to be even more conservative, you can measure it further down right before it gets to the entry point of being distributed out. And that will give you a safer bet, a more conservative estimate of the concentration of your chlorine or your disinfectant that's in your contact basin. Okay, and you're going to hear that theme a couple times, where when we're in doubt, we're always going to estimate a more conservative estimate in order to ensure that we're always underplaying what our potential CT is, so that we're not giving ourselves too much credit or overestimating the amount of disinfection we're getting. Because if we overestimate, then we could actually be under-treating our water and making it less safe than we think it is. So, so it's better to kind of err on the side of caution, underestimate your C values. We'll look at how you might underestimate your T values a little bit, so that you are erring on the side of caution with the calculated CT and making sure that you're achieving the disinfection needed to actually hit your log credits. So you'll see that concept come up a couple times. Okay, so that's how we get C. You measure it at the outlet of your contact, take a sample. There's different methods for measuring chlorine. You might be familiar with the DPD method, where you've got a pouch, you add it to your sample, it changes color, you measure the color, the depth of color, and that gives you a reading in milligrams per liter. Okay, so that's C. T requires a little bit more work, and it has to do with the type of basin in which your chlorine is going to be in contact with the water. Okay, so and some of the things that come into play are the shape of the vessel, so whether it's a cylinder versus a rectangle, and whether or not it has baffles. And so, for example, baffles like this help increase contact time, right? Like the water has to spend more time in the tank if it has to flow through and around these different baffles. So we'll look at how that plays a role in calculating our T. So how you get T, there's a couple different ways, and the first way is you get something called a T10, and you get it from a residence time distribution curve. So a couple of terms here that you might not be familiar with. What's a T10? What's a residence time distribution curve? So we'll talk about that in a second. The second way, which we'll get into afterwards, is that you can calculate it using flow rate, using the volume of your basin, and something called a baffling factor, which has to do with the type of baffles that you have in your contact tank. Okay, so what's a T10? Well, before we get into that, just a quick kind of side note that might help clarify. So let's say you're adding water to your contactor, or you're adding it to your contact basin. What is probably not going to happen is, as your water flows through that contact tank, it's probably not going to flow in single file order like we just saw in that animation there, where every droplet of water spends exactly the same amount of time in the basin before it exits. That's not realistic. That's not how water flows. That is called ideal plug flow, but in reality, water can bypass the normal flow path. It can short circuit. Some water might come out really early. Other might get caught up in an eddy somewhere and be lost in a dead zone and take a lot of time to come out. And so because of that, what you actually end up with is a distribution of how much time water spends in your contact tank. And so, I lost my, there, okay. Hopefully you can still see the screen. My screen went a little glitchy. So what that looks like is a residence time distribution, or something that looks like this. What this is doing is looking at how long different amounts of water spend in your contact basin. And how you get something like this is through something called a tracer test. So what you could do in like the manufacturers of these contact basins, they might add some dye into their inflow that goes into your contact tank. And then at the outlet, they will just look at how long it takes for the first drop of dye to come out versus how long it takes for all of the dye to come out. And they're just taking samples and collecting how much dye is in there. And they might end up with a curve that looks like this, where some of the water comes out right away, or some of the dye might come out right away, and some takes a lot longer to come out. So because we have a distribution like this, it's hard to know how you use one number to say, this is how much time the water spends in my contact basin. And so again, if you're given an RTD like this from a manufacturer who says, this is the residence time distribution of this contact basin, to be conservative, to err on the side of caution, we're not going to say that, oh, all the water spends 200 minutes in this example in my contact basin. That would overestimate the amount of time that it spends, because we know that there's a bunch of water that comes out much faster than that. So to be cautious, we're going to use what's called the T10. And the T10 is taken as the time that the first 10% of water makes it through. The fastest 10% makes it through. And so that should be provided by a manufacturer, should be given to you as a T10 value when you purchasing the contact tank, or whoever designed the contact tank, or you can reach out to them. They should be able to give you that number. And if you have that, then that can directly be used as your T value for calculating CT. So you have the C for measuring the concentration, then you get the T from this T10 number from the manufacturer of your contact basin, and then you're good to go. Okay. Let's say you don't have an RTD, you don't know what that residence time distribution curve looks like, you don't have a T10 value, then what do? Well, you can estimate and calculate T using something called a baffling factor. And the baffling factor method requires you to do a few calculations, but they're relatively straightforward. And so we'll just list some of these steps. The first thing you need to do is calculate the volume of the contact basin. And so depending on the shape of your basin, there are a couple formulas you can use to calculate that. Then you want to measure the peak hourly flow rate through the contact basin. This is the max flow rate. At the max flow rate, your water is going to spend the least amount of time in your contact basin. So by using your max flow rate, again, we're using a conservative estimate. You're going to use those two to calculate the theoretical detention time. This is the amount of time, in theory, that an average amount of water should spend in your tank. Then you're gonna look up what's called a baffling factor using a table. These tables are in your drinking water guidelines, and we'll look at one in a second. And then use that to calculate T by multiplying this theoretical detention time by the baffling factor that you look up. Okay, so we'll go through an example that kind of walks through each of these 5 steps. First, to calculate the volume of your contactor or your basin, it's really a matter of just looking at it and seeing, is it a cylinder, is it a rectangular basin? And then based on that, you can use the volume calculation, either pi r squared h, where r is the radius of the tank, h is the height of the tank, or length times height times width. By getting the dimensions of your tank, you can then calculate the volume. So you want to calculate the volume of your basin. You might even just have the volume if you know what it is from the manufacturer. Then you want to know the flow rate. Ideally, you have the flow meter that's being used to measure the flow rate going in to your contact basin. And you want to use the peak hourly flow rate. Like I said, we're trying to use the worst case scenario to give us the most conservative estimate of our T for our CT. So at the highest flow rate, the peak hourly flow rate, you're going to get the lowest amount of time in your contact basin, which when you multiply by C is going to give you a relatively low CT, a more conservative CT, so you don't overestimate how much disinfection you're doing. Okay, so you're going to use that. Together, the V and the Q, which is the flow rate, those are going to be used to give you your theoretical detention time. Okay, so you get that from taking the volume and dividing by the flow rate. So quick example here, let's say you have a chlorine contactor, it's got serpentine baffles. That's not important to us yet, but we'll get to that in a second. But it has a volume of 250 cubic meters. Okay, so we have the volume, that's our V, and the peak hourly flow rate is 2 cubic meters per minute. So if I look over an hour, what's the maximum flow rate that I observe? The peak maximum flow rate, the Q value, 2 cubic meters per minute. I also get some information on the residual chlorine. Good to know, we'll use that later. But right now, all I need is V and Q, right? So V 250, Q is 2. So my TDT, I'm just gonna divide V by Q, 250 divided by 2. Make sure that my units all work out. So I've got cubic meters and cubic meters. Then my theoretical detention time is going to be 125 minutes, meaning in theory, water on average should spend 125 minutes going through that contact tank. Okay, so that's how you calculate TDT. That's step 3. Step 4 is using a table like this one to determine your baffling factor. So based on the description of the baffles that you have in your tank, either you might have no baffles at all, it just goes into a tank and out the tank, there's no baffles in that tank, then your baffling factor would be 0.1. You can look through the different descriptions and then based on that, assess what the baffling factor might be for your contact tank. So in this case, in our example, we're saying the contactor has those serpentine baffles. That's the kind that we saw in the picture where the water kind of flows back and forth like a snake. That's where the name comes from. And in this case, we see that that gives us a baffling factor of 0.7. So we're looking up the table, finding the description that corresponds to what we're using, and then selecting the baffling factor based on that. So now we have that value. To get T in this case, multiply the TDT that we just calculated by our baffling factor. So we can take the 125 minutes multiplied by 0.7. In that case, it gives us a T value of 87.5 minutes. Okay. To get CT, now we know that our chlorine residual is 0.8 milligrams per liter. We can then multiply that by our T value, which is 87.5 minutes. By multiplying those two, we get our value of CT in milligram minutes per liter. Again, always make sure that you're checking the units. You might need to do a unit conversion. But in this case, our CT value that we calculate for this system is 70 milligram minutes per liter. Okay, so we calculated CT. So that's what we have. Now, how much removal is that actually giving us? Well, that's going to depend on our drinking water guidelines and what pathogen we're targeting. So let's say we're trying to get rid of Giardia and we want 3 log removal of Giardia. And let's say our conditions where this example is taking place is a pH of 6.5 and the temperature is 0.5 degrees Celsius. Okay, so we go to our guidelines, we look up our CT tables and we say, okay, for 0.5 degrees Celsius, pH of 6.5, and my chlorine concentration is 0.8. Saw that in the earlier slide. So the CT that I need for 3 log removal is 172. Okay, I need 172. What I have is 70. So based on that, I know that I'm undershooting for 3 log removal. And then the question is, well, how much credit can I get for log removal based on having 70 instead of 172? Okay, so to do that, the credits that you get, or the log credits that you can say that you've achieved, are determined by dividing the CT that you've calculated for your system by what's in the table as being required for 3 log removal and the amount that you get credit for if you were to achieve that required CT. So in our case, we calculated that the CT that we're getting is 70. What we need for 3 log removal is 172. And so by putting those values into this equation, we can see that we don't get 3 log removal, but we are getting 1.2 log removal from our system right now. So that's how many log credits we have. Okay, so let's put everything together into one example and see if we can calculate CT and calculate the log credits needed. Okay, so let's say you're targeting a CT value of 90 milligram minutes per liter. So that's the CT that you want in order to get 4 log removal for viruses. And you take a sample at the outlet of your contact tank and you measure that the chlorine residual is 1.5 milligrams per liter. And then you measure the water flow rate to be 2 cubic meters per minute, and the contact basin volume is 300 cubic meters. The contact basin has a baffle at the inlet and some baffles inside. And the question is, what is the calculated CT value? How many log credits have you achieved? So if you want, you take a minute and try to work on this, and then we'll work through this. So maybe just take a minute, look at what information you have. Maybe you can identify where your volume is, where your flow rate is, the residual concentration. See if you can quickly come up with a response for this. Okay, that's about a minute, not too much time, but we'll walk through the example and hopefully you had a chance to make some progress towards this. So first, let's just identify what we have in terms of information. We know the concentration measured at the outlet of the contact tank, that's our value for C. We know the volumetric flow rate, so that's our value for Q. We know the volume of the contact basin, that's our value for V. So right away, we can use our V and our Q to calculate our theoretical detention time. So we take that 300 cubic meters, divide out the volumetric flow rate, 2.2 cubic meters per minute. That gives us our theoretical detention time, 133.33333 minutes. We can look up our baffle table. We see that it has a baffle at the inlet, some baffles inside. Based on looking at our description here, it's not serpentine. We don't have perfect plug flow, which requires a very high length to width ratio, like a thin pipe. but we do have some baffles. So it looks like baffle inlet or some outlet, or either baffled inlet or outlet with some intrabasin baffle seems to be the right one. So our baffling factor is going to be 0.5. We have our TDT multiplied by our baffle factor. That gives us our T value, which is the equivalent of our T10. That's 66.67 minutes. So now we have T, we also have C from our question. So we can multiply those two values and we get our CT value, 100 milligram minutes per liter. Now we know from our table here, we're targeting 4 log removal of viruses. It requires 90 milligram minutes per liter of CT. So how many log credits are we getting? We can divide that from our calculated CT multiplied by 4 log removal, which is what we're targeting. And we know that because 100 is bigger than 90, if we're actually exceeding that, we get a little extra credit. So we're meeting our 4 log removal that we're aiming for. Okay, so that was a quick example going through kind of from start to finish the steps in calculating your T value, and then using the C with the T to get CT, and then based on that CT and what you're aiming for in terms of log reduction of a particular pathogen, how you can determine the log credits that you have. Okay, so a quick summary of what we covered. So CT is basically looking at how effective your disinfectant is, and it's determined by the concentration of the disinfectant, which is measured at the outlet of the contact tank, and the time that that disinfectant spends in contact with the microorganisms in the water. And T, that time, is taken as the first 10% of the time that the first 10% of water leaves a contact tank, according to a residence time distribution curve, also known as a T10. And again, if you don't know that or not given that by a manufacturer of your basin, then you can estimate it using some calculations, knowing the volume of the tank, the peak flow rate, and the baffle factor based on how many baffles you have in your tank. Once you know that, you can look up the CT required to achieve a specific log removal for a pathogen. You can look that up in the drinking water guidelines. And then based on that, you can compare it with your calculated CT to figure out how many log credits your system is achieving. And then we went through an example that kind of showed all that. Okay, so I'm going to end it there. That's basically covers the concept of CT, and happy to take any questions that folks might have.
Pranav, thank you for that presentation. That was excellent. Yes, we're going to open up to questions. If people can type their questions, we will try and answer them. We do have a couple of questions here. We have a question. If an operator doesn't have a flow meter, can you provide some insight into how they can estimate the peak hourly flow?
Yeah, that's a tricky one. I mean, okay, so you don't have a flow meter. Ideally, you have some way of assessing how volume of water is changing with respect to time. So if your inlet pipe is entering your contact tank, or you have some way of drawing a line off of that in order to collect some volume of water, you can see how long it takes for a certain volume to fill up, depending on the size of your system. It's a very large system, obviously that becomes more difficult to do. If it's a small system, then maybe you have a large enough vessel that you can use to collect a volume of water, and then you can use a stopwatch to see how long it takes to fill up to a certain known volume. And then based on that, that can be used to calculate the volumetric flow rate. So the amount of volume that you're able to collect over a given amount of time, either a minute or some seconds, you can use to then calculate a volumetric flow rate. Off the top of my head, that's what I would suggest, depending on the size of your system, if that's possible. Yeah.
Well, good stuff. Thank you. We have another question here. In addition to primary chlorination, in addition to the primary chlorination step going into the contact tank or reservoir, some water systems have recirculation loops with ORP meter and secondary chlorination step that serve to keep chlorine levels at a consistent concentration. How would this be factored into a CT calculation?
Yeah, so that's all happening ahead of the contactor, it sounds like. Is that right? If I understood that correctly? Or it's a recycle from the outlet coming back into the inlet, is that?
I'm unsure by the question, actually, sorry for now.
Okay, no worries. So in either case, let's say it's recycling from the outlet of your contactor and going back to the inlet, or it's just recycling at the inlet. In either case, you want to be taking your sample downstream of that, because what's really important is that you're measuring the CT value, the C value, based on the residual concentration of chlorine that's then being distributed out to your distribution system. So in either case, I would take it after that point and before it then enters your distribution system.
Okay. We have another question, and it says, for tables, what do you pick when you have a value between what is shown?
Yeah, it's tricky in that case. You might need to do some interpolation. I didn't go over that in case, yeah, for example, you're somewhere in between what the table is showing you, you need a value in between, and it's not necessarily closer to one or the other. In one way, you can use interpolation to try to calculate a value that's in between. A better way might just be to take the more conservative estimate. So I would err on the side of caution, give yourself the lower CT value, or if you're targeting a CT, I would aim for the higher target. And that way you're underestimating the disinfection that you're achieving, but it ensures that you're then compensating in some way, either by increasing your chlorine dose or increasing your contact time, in order to then give you the amount required to get the log credits that you need. You always want to tend to err on the side of caution when it comes to CT. As far as like increasing chlorine dose, obviously there's limits to that. You want to be mindful about the residual that you're getting afterwards. So contact time might be the safer thing to try to increase, either through the use of baffles or adjusting your flow rate if you can. Because you may not, there's an upper limit to how much chlorine you want to be adding to ensure that you have a safe amount of residual going out to people's homes.
Okay, thank you. We have another question here with regards to breakpoint chlorination and its relation to CT, and are they completely separate concepts from each other?
Yeah, it's a good question. So breakpoint chlorination has to do with if you're using chloramines, you're adding free chlorine and it's reacting with any ammonia that's in the water to form your different chloramine species, or it's reacting with other substances in the water, so it's using up that free chlorine. So you get that kind of breakpoint happening, and then your free chlorine amount is increasing afterwards. And that really just has to do with you're adding chlorine, it's reacting, the amount of free chlorine getting used up until all those reactive species have formed, and then you have the free chlorine that's available to do the disinfection. It's not entirely a different concept. So in the case of how breakpoint would affect this, it's really about the residual chlorine that's left over after your contact basin. So once you're supplying free chlorine, you're making sure that you're adding enough to overcome any species in the water that are going to react with that. That happens when you take a sample, you go to your lab or whatever, you quickly figure out how much free chlorine dose you need to overcome that in order to ensure you have some free chlorine residual. Once you know what that is and you dosed it, it's gone through the tank and you see what your residual is afterwards, that's really where you get the C value that you need to calculate CT. So it's related in the sense that you need to know where that breakpoint is to know how much chlorine you need to add in order to then assess later on downstream what the residual chlorine amount is.
Okay. We have another question here. It says, tagging on to the recirculation question, would the calculation for T be affected?
That's a good question. What I would suggest is your boundary in which you're assessing the inlet versus the outlet should encompass that circulation. Okay, so if you're recirculating, I wish I had a blackboard so I could draw. if you're recirculating, imagine you have a tank, right? And what I'm picturing you're describing is that at the outlet of your tank, you're recirculating back to the inlet of your tank. And then that's affecting your dose of chlorine. What I suggest is, what did I do? I zoomed in on my face. My camera responds to hand motions and zooms in sometimes. What I suggest is that your boundary between your inlet and your outlet has that recirculation within it. So if you were going to draw a box, maybe I can use my slide to help describe this. So I'm going to go back to, if I'm interpreting the question correctly, let's say you have a recirculation from this outlet here, and it's coming back into your inlet of your tank. That's kind of how I understand it. The boundary of your inlet versus your outlet, imagine that being a square that encompasses that recirculation. So then the outlet is downstream of that. And so with that in mind, I would look at the flow that's entering and the flow that's exiting, and you could use your exit flow as your Q value to then calculate your T in that case. But it is true, there's water that's now re-entering. So in a sense that you're getting a longer contact time as a result of that, because water is getting more time to spend, and you're supplementing with chlorine. So you're getting more contact with chlorine. It would definitely increase your contact time, increase your CT. So in that case, that recirculation would have a beneficial effect in terms of disinfection for sure.
Okay, we do have another question here. In the case of some old and existing irregularly shaped clear wells / contact tanks, what are the other ways to better determine the baffling factor in lieu of relying on descriptions alone?
Yeah, that might be a little trickier. So baffle factor, what it's doing is trying to indirectly estimate your T10. And in that case, if you've got a unique situation, you may benefit from trying a tracer test if you can. That might require taking the tank offline in order to do that, because you don't want to do that while your system is running, and even if you're using a benign dye. But assuming if it's old and irregular, then you may not be able to get in touch with whoever manufactured it. So what a tracer allows you to do is basically look at how much time a particular liquid is spending in your tank and the distribution of that. Then you can make your RTD curve from that based on collecting the dye at the outlet and see how long it takes for all that dye to come out. And then based on that, you can then figure out where that 10% T10 is located. Baffle factor is just an indirect way of doing that by giving you a conservative estimate of what your T10 would be based on an understanding of how your baffles are set up inside your tank. So if it doesn't match the table and the descriptions that are in that table in order to give you a quick estimate, then you could try something more sophisticated like a tracer test. Yeah.
Excellent. So far, that's all we have for questions there for now. We'll just leave it for a pause here for 10 seconds to see if anybody else has a question, and then we'll thank you. It appears we have no more questions. Pranav, thank you very much for your presentation. It was really interesting. It will actually help me out in the work that I do. Thank you for that.
No problem. Thanks for having me. And my email is here on this title slide, if you can still see the slides. So feel free to email me if any questions come up. And I'm happy to share this slide deck to the organizers if it can be distributed. I'm happy to do that. So yeah. Thanks
Excellent.
again. Thank you.
Thank you very much, everybody.